Hi, everyone. Thank you for attending this important session here. Before I begin, let me thank the following investigators for sharing their data over the years. And I would like to also acknowledge collaborators of Project Integrate. And this project wasn't going to be possible without the generous support from NIAAA. And I'd like to thank my program officers, Aaron White and Mariella Shirley. Thank you, Mariella, for coming. In this talk, I would like to provide some background for our work and promise and pitfalls of using individual participant data. It's an exciting opportunity, but at the same time, it can be very dangerous in some ways. And I'd like to also introduce the approaches we have taken in the past. This talk will be more conceptual rather than technical. And if you have any questions about specific questions and technical aspects of it, please feel free to email me or talk to me after this session. So now these are background. Iconic articles that challenged us to strengthen our standards for clinical trials and empirical research. So in these articles, meta-analysis was suggested as one of the new directions that we can use as a response to the crisis in waning public trust in empirical evidence. But at the same time, this was happening. This is a figure of how popular meta-analysis has been from 1975 to 2010. So for about 3 decades or so, the green line indicates sheer number of publications that use meta-analysis as a method, and the one on the right is a proportion of studies published using meta-analysis. So the dotted line below, those are the papers published using structural equation modeling as a method. So as you can tell, that structural equation modeling has been extremely popular in the field, but it pales in comparison to meta-analysis. So meta-analysis has been extremely popular. It normally it normally gathers a lot of citations, so it has been extremely influential in the field in terms of designing clinical trials, in terms of having a conclusion. So we have a very important task here that we have to get it right in terms of meta-analysis and its conclusion. This is another figure also shows the popularity of meta-analysis. The blue, red line indicates systematic review. The red one indicates quantitative meta-analysis studies. So it has exploded again from 1986 to 2015. So with the rising importance and popularity comes the concern that there are suboptimal reviews and meta-analysis that are misleading, redundant, or even harmful. So we have to do better. So in my field, which is the area of young adult alcohol intervention studies, I have encountered several meta-analysis studies with divergent conclusions, sometimes very drastically different ones. So in one case, we challenged their meta-analysis study for their methods as well as results. As a result, it was withdrawn. But the main challenge remains. The challenge is, how do we create a healthy ecosystem within which every stakeholder contributes to the system and benefits from? So if we can provide a good overview of the area with little to no evidence or conflicting findings, it will benefit individual investigators in their way of planning new studies. And in return, with their results from their studies, we can combine the data to help make important decisions for treatment strategies and intervention strategies. So this is my ultimate goal. So Project Integrate is at the crossroad for major stakeholders, including adolescents, young adults, parents, college administrators, and NIAAA personnel to NIAAA. So Project Integrate was originally launched in 2010 as an integrative data analysis project where we combine individual participant data from multiple brief alcohol intervention trials for college students. And we have encountered many challenges. And as a result, we expanded our scope dramatically in recent years. So obviously, now we have multiple dimensions to our study. We now think of the project in much broader terms. First, we realize it's necessary to add aggregate data into our study goal. It can provide more breadth as well as depth that we get from IPD. IPD is the only data that can provide the most granular information. In our case, we have item level data, so it provides breadth and depth. And also, we think of our project instead of integrative data analysis, but as a meta-analysis of AD plus IPD. I will explain the difference between IDA and meta-analysis in the next slide. And second, we also realize it's necessary to develop our own methods to be able to achieve what we want to achieve, and disseminate them via data analysis examples. In short, we attempt to synthesize across multiple domain behaviors, across multiple studies, and multiple related domains can be many things, including multiple treatment arms or competing interventions, as well as different outcome measures, related outcome measures, longitudinal data, as well as related covariates. And only by combining all these, we can generate model-based estimate that get us to precision medicine. So first, I want to provide how IDA is different from or similar to meta-analysis, and how our approach is different from either one. So IDA is an approach of analyzing data from multiple data sets as if it were from a single data set. In this table, rows indicate different studies, and columns indicate different variables or coefficients. In meta-analysis field, data is often referred to as a treatment effect size. So I use data 1.1, data 1.2. So data 1.1 can be treatment effect for study 1 for, let's say, alcohol quantity. Data 1.2 could be the effect size of study 1 for alcohol frequency, and so on. So you can see frequency, quantity, problems, they are all related. So how do we combine it? Anyway, in the IDA analysis, but it's not about that though. In IDA analysis, since it is pulled together, data are pulled together as if it's a single data set, it doesn't acknowledge the data structure that exists within the data set. So what we get in the end is as if individual participant data came from a single study by harmonizing the items. So what we get is the relationship that exists within the data set across the studies. So if we have some kind of accordion, you flatten it, and we have a one results at the end that's an average. So we have a data 1, data 2, data 3, regardless of study. That's an IDA. So ideally, it sounds nice. We can examine the related coefficients across studies, but there's strong assumptions involved about the data structure, and that is being relatively less well treated in the IDA. So we stay away from the approach where we combine or pull data without paying attention to the data structure. So standard meta-analysis, on the other hand, we combine data across a study, one at a time. So each of the columns would indicate overall effect size. Okay? So we combine the data, but it respects the data structure that exists across different studies. Note that I use the word pooling for IDA and combining for meta-analysis studies. Similarly, I use the term average coefficients to describe IDA outcomes, but I would use term weighted average for describing combined data from meta-analysis. These are very different concepts, and there are statistical differences between the two approaches. So Project Integrate is trying to do combining data across multiple domains, multiple dimensions for study by variables. So the direction we need to strive toward is multivariate synthesis, where we combine both studies and variables at the same time. This represents tremendous opportunities as well as potential pitfalls. So let's first talk about the promise. Okay, promise of using IPD can be, it can produce large-scale evidence. It can utilize item-level data. It can access more data than what's been reported, and it's true. I've seen many more data than reported. More important, we can check clean data as well as accommodate missing data at the individual participant level. And we can also utilize same inclusion-exclusion criteria, which is evasive in other techniques. And also we can utilize same analytical model, can have the same interpretation of parameter estimate because we use exactly same criteria for inclusion, exclusion, as well as same analytical model. So resulting estimate could be ecologically valid and clinically most useful because we use a valid approach to analyze the effects of different coefficients. Also, we can conduct new data analysis to address new questions when it's called for. However, these advantages are not without caveats. Some of the challenges are, although IPD allows missing data handling at the participant level, it will create missing data at the study level. And same interpretation from the same model can be very difficult to achieve, which we will explain further. In addition, ecologically valid and clinically meaningful inference may be possible only for a subset of the data. Before we go further, let me explain also two basic meta-analysis models. One is random effects meta-analysis model, and the other one being the fixed effect. First, for the random effects meta-analysis model, we assume, okay, top one indicates the overall effect size. The bottom one indicates at the individual study level. So overall level, individual study level. The bottom one, the red indicates, red dotted line indicates sampling variability. And then the blue arrow indicates it's a study-to-study variation in effect size across studies. So within this scheme of things, each study has its own ground truth regarding effect size. Some studies will have higher, greater effect size. Other studies will have a poorer effect size. And there's a natural variation across. And to accommodate all this variation, tau square, which is a between study heterogeneity, will have to factor in. On the other hand, in a fixed effect meta-analysis model, there is a ground truth that is shared by all studies. So it assumes there is only one common effect size across all the studies. And any variation in effect sizes across studies is simply due to sampling variability of individual studies. So you see the data is shared by all the distribution. That's fixed effect model. The random effect meta-analysis model is based on more reasonable assumption, as you can tell, about effect sizes and between study heterogeneity. But the sources of between study heterogeneity are rarely accounted in real meta-analysis. So typically, any between study differences tend to be swept under between study heterogeneity estimate tau squared without actually going into detail about explaining it. So IPD is the only approach that allows you to actually examine what exactly happening about different effect sizes. So with IPD, with multivariate meta-analysis, we can actually examine. So this is a general formula, extending the univariate standard meta-analysis into a multivariate form. So here, level 1 is the study level. Level 2 is the overall level. So it follows exactly the same form as before. Only thing different here is we are not talking about individual coefficient like treatment effect size. We are talking about a string of effects that are related. So treatment effects, gender differences, age differences, setting differences, all coming from same study and then combined across. So that's a multivariate synthesis. And because of this related formula or equation or prediction model, we can actually predict what were to happen if we have X and Y and Z. So that's one step closer to precision medicine model of treating alcohol problems for young adults. Now, having said these new opportunities come with challenges and potential pairs. So combining AD or IPD can go wrong very fast. First, IPD or AD can be confounded with study level differences. One such example, it can happen for many reasons, but I'll give you one example. Studies aimed at improving high-risk individuals with more severe depression, for example, may have used PHQ-9, which is a diagnostic screening tool, rather than the CESD, which is a more normatively used. Similarly, in the alcohol field, audit may be used instead of YAPST, which is used for more normative behavior. So the measurement differences across studies can be confounded with study level effect size differences. I will skip this part. Anyway, to combat this problem, what we have done is we have used MCMC and IRT model. We coded ourselves and then tried to validate ourselves to see if it works and then do the real analysis. It can go wrong very fast for this reason too. Some studies could include all men or all first-year students. In that case, intervention effect sizes from these studies do not have the same meaning relative to the rest of the studies. So let's specifically think about alcohol-related problems at post-intervention predicted by whether somebody received treatment or not, plus gender difference, right? So let's focus on intercept. In the first case scenario, study include both men and women, okay? So treatment and control were coded as 1 versus 0. Men and women was coded as 1 versus 0. In that case, intercept value would indicate it's the level of women's alcohol problem in the control group at a follow-up. But in the case where all men were included in study, it would indicate men's alcohol problem at a follow-up in the control group. So this coefficient, although it may share the same B0, it doesn't carry the same meaning across studies. So design difference can make a big difference in terms of what we are getting. Okay? In addition, it also means treatment effect size also carries different meaning. So again, if we have also two different interventions, it can also have a different meaning in terms of beta 0, beta 3, and beta 4. So to make this comparable, what we have done before is that we come up with a method called mapping to be able to match individual study estimates to the overall effect size estimate. We did a mapping. So we often talk about measurement equivalence as one of the big elephant in the room for IDA, but it's only a tip of an iceberg in our experience. So study level missing data is also another problem. This doesn't look too bad. The rows indicates variables, columns indicate studies. It looks like X indicates we can estimate those. It looks like we can estimate a lot. But if you look at it closely, you only realize only one study has everything. And if that's the case, it wouldn't be a synthesis because the only one study is possible to do this analysis. So there has to be some way we can compensate the study level missing data. That's why we use a mapping method to be able to connect the dots. So after ensuring that we can have a same interpretation, how do we combine data? We have used 3 different techniques. One was we combine data from different studies as if, okay, it's from a single data set, except that we accommodate design effect in the analysis by specifying clusters and weights. Right? So study membership become a cluster variable, and weights was provided to make sure that bigger studies does not overly dominate the estimation of parameters. Because if you have more cases in bigger studies, it will dominate the entire overall estimate. So we try to do that. And second one is a 2-step IPD meta-analysis, where we got the data from different data sets, analyzed separately, and then we get the regression coefficients in a vector. We combine them in the second step. And third approach will be was to analyze them simultaneously in one step, which will be described in a greater detail in the next talk. So these are some of the examples, data examples, or studies that we produce using different approaches. Okay, 3 different approaches. So having said what we have done, it may be worthwhile discussing what we have not done thus far deliberately. One was to pull data without incorporating the design feature of the pool data set, which is quite commonly done in IDA. Second, we try to avoid breaking the randomization of the original studies. Number 3, we try to avoid using scale scores as if they were item responses. We try to reflect the measurement characteristic as much as we can. And then fourth, we avoided analyzing IPD separately and reporting them separately. So what we are working on many fronts, we plan to have a website up and upload all the useful information this year. Thank you for listening. And if you have further questions, please feel free to email me or talk with me after this.